Hi there, fellow experimenter. My name is John. I'm a retired pensioner very interested in physics. This presentation will cover the following topics: the physics involved in the lab, the experimental setup and tracker configuration, the computational model configuration and its execution in Python, comparison of the predicted against the actual results, and what if and what does it all mean scenarios. This lab will observe the horizontal motion of a moving body under constant velocity. This means that the body will neither change speed or direction. The motion of the body will be in a horizontal direction. The only external forces on the body are friction, the forces between the surface and the body, and the effects of gravity on the body. We assume that the frictional forces are negligible and the weight of the body and reactive force of the body on the surface cancel out. The motion of the body will follow Newton's second law as illustrated here. From this equation, we can derive the velocity equation, which gives the final velocity based on force interactions, time and initial velocity. That's this equation here. The net force on the body is 0, and consequently, the equation reduces to the final velocity equal to the initial velocity. Vf equals Vi. The position of the object is given by the last equation. We will observe the motion of the body through the use of the tracker. A glass ball is rolled across a flat kitchen surface. However, some initial bounce of the glass ball was noticed and a little time was allowed at the beginning to allow the ball to stabilize. The calibration stick is a tape measure stuck onto the wall. The tape has alternate yellow and black intervals at 10 centimeters each. The coordinate system origin, 0, 0, was taken at the center of the glass ball at the intersection of the axis shown. I tracked some time after the ball had started rolling to ensure stability of motion. The ball moves in a negative direction along the x-axis. The axis origin is located at the center of the ball. The modeling parameters extracted from the observed data are shown here. The start and the end time of the body's motion and its initial position are given. The initial velocity is taken from the first two positions and time entries recorded by the tracker and calculated as shown. This data will be entered into the Python script that models the motion. The parameters described in the last slide are now entered into the Python script. This includes the mass, the initial position of the ball, the velocity of the ball, the initial velocity of the ball, a small time increment, the time limit on which the simulation runs, and the net force acting upon the ball. This is important for this equation here, since this reduces this equation, the right-hand side, to the initial velocity being the same as the final velocity. The ball position is then recalculated. We will now run the Python script. As we can see, the ball moves from left to right, and the graph indicates it moves in the negative direction according to our axis. The position and time can be seen to form a slope, and this indicates the velocity of the object, which is negative. This is a plot of our observed data with our predicted data. The items in red are our observed data, and the items in blue are our predicted data. Initially, we find that the correspondence between observed and predicted is quite close. However, towards the end, we see the two plots diverging. I believe this due to the fact that it wasn't completely a straight line motion towards the end and veered off towards one direction. I hope this explains it. Flipping the axis causes recorded positive positions to become negative values and negative values to become positive. The magnitude of the positions remain the same, although the signs change. The velocity direction reverses, but the magnitude of the velocity remains the same. The motion of the ball as depicted by the graph in Python remains the same. However, the velocity graph is a mirror image in the x-axis. The weight of the body, or the force due to gravity, and the normal force of the body on the surface cancel one another out. We assume that the frictional forces are negligible but non-zero, eventually causing the ball to slow down.